Right now, somewhere in the universe, there might be a civilization using the entire energy output of their star. Not solar panels on a few rooftops, not a fusion reactor or two, the entire star wrapped in a shell of energy-collecting satellites, drinking in every photon that radiates into space. We're talking about a power source 2 billion times more potent than everything Earth receives from the Sun. Enough energy to move planets, to create artificial worlds, to become visible across the galaxy as a monument to cosmic engineering. And here's what keeps astronomers up at night. The physics allows it. There's no law of nature that says you can't do this. It's difficult, sure, but not impossible. Which means if intelligent life is common in the universe, these civilizations might be out there right now, harvesting stars, colonizing galaxies, operating at scales that make our entire civilization look like a candle flame next to a bonfire. But here's the thing, we haven't found them. The universe is 13.8 billion years old. The Milky Way alone contains 200 to 400 billion stars. If even a tiny fraction of those stars hosted intelligent life, if even a handful of those civilizations survived long enough to master their star's energy, we should see them. They should be obvious. They're not. So either we're looking in the wrong places, or there's something stopping civilizations from reaching these godlike scales. Something we haven't encountered yet, or something we're about to face ourselves. Because humanity isn't sitting still. We've gone from burning wood to splitting atoms in just a few thousand years. We're climbing a ladder of energy consumption, moving from planetary resources towards something bigger. Much bigger. The question is, how far up this ladder can we actually climb? In 1964, a Soviet astronomer named Nikolai Kardashev proposed a way to answer that question. He created a scale, a cosmic hierarchy that measures civilizations, not by their culture, their technology, or their values, but by something far more fundamental. Energy. How much energy can you harness? How much power can you control? Because in the universe, energy isn't just about keeping the lights on. Energy is capability. Energy is reach. Energy is the difference between a civilization bound to one planet and a civilization that can reshape solar systems. Kardashev identified 3 types of civilizations, 3 levels on this cosmic ladder, and when you understand what each level can actually do, when you see what's physically possible if you can just gather enough power, it changes everything. But here's where it gets personal. Where do we fit on this scale? Where is humanity right now? We're not type 1. We're not even close. We're something called type 0.73. We're still burning dead plants for energy, still fighting over resources on a single planet, still figuring out how not to destroy ourselves with our own technology. And the gap between where we are and where we need to be, it's staggering. So where are we on this cosmic ladder? What does each level actually look like? What can you do when you harness a planet's energy, a star's energy, an entire galaxy's energy? And maybe most importantly, what happens to civilizations that try to climb? Because if star harvesting societies exist, if galaxy-spanning empires are out there, we should see them. The fact that we don't, that's either the best news possible or the worst. To understand what we're looking for and what we might become, we need to talk about the scale that started it all, the framework that transformed how we think about alien civilizations and our own future. We need to talk about Kardashev's ladder. The year is 1964. The Cold War is in full swing, and both superpowers are racing toward the stars. The space age is barely 7 years old. And in the Soviet Union, an astronomer named Nikolai Kardashev is thinking about a problem that most of his colleagues consider, well, a bit premature. He's trying to figure out how to find aliens. Now, this isn't as wild as it sounds. Just 4 years earlier, American astronomer Frank Drake had conducted the first serious search for extraterrestrial radio signals. The idea of searching for intelligent life was moving from science fiction into actual science. But Kardashev had a question that no one had really addressed yet. If we do detect a signal from an alien civilization, how do we understand what we're dealing with? How do we measure how advanced they are? You can't judge by their culture. We wouldn't understand it. You can't judge by their technology directly. We might not recognize it. You can't judge by their art, their politics, their philosophy. So what can you measure? Kardashev's answer was elegant. Energy. Energy is universal. It doesn't matter what language a civilization speaks, what values they hold, or what their biology looks like. Energy consumption is something you can observe from light years away. And more importantly, energy consumption correlates directly with capability. The more energy you can harness, the more you can do. It's that simple. Think about it. A civilization that burns wood can keep warm and cook food. A civilization that harnesses coal can power trains and factories. A civilization that splits atoms can power entire cities and send robots to other planets. Energy is capability made measurable. So Kardashev proposed a classification system. 3 types of civilizations, each defined by the scale of energy they can control. Type 1 controls all the energy available on their home planet. Every ray of sunlight, every bit of geothermal heat, every joule of energy their world receives or generates. Planetary mastery. Type 2 controls the energy of their star, not just what reaches their planet, but the entire output of their sun. Stellar mastery. Type 3 controls the energy of their galaxy. Billions of stars coordinated across tens of thousands of light years. Galactic mastery. Each level is exponentially more powerful than the last. We're not talking about incremental improvements here. Each type represents a fundamental leap in scale, in what you can do, where you can go, what you can build. And here's what made Kardashev's scale revolutionary. It gave SETI researchers something concrete to look for. If a Type 2 civilization exists, they're building structures around their star. Those structures would have signatures we could detect, even from thousands of light years away. They'd glow in infrared. They'd create patterns in the light we observe. If a Type 3 civilization exists, they're visible across the galaxy. You can't hide that kind of operation. The engineering alone would be unmistakable. Kardashev's scale transformed the search for extraterrestrial intelligence from let's listen for radio signals and hope to let's look for specific physical signatures of civilizations at different scales of development. It gave us a roadmap, a framework for understanding not just if life exists out there, but how advanced it might be. Now, Kardashev's original calculations for each type have been refined over the decades. Scientists have argued about the exact numbers, proposed modifications, added new categories. But the core insight remains. Civilizations can be measured by their energy budget, and that budget grows exponentially as you expand your reach from planet to star to galaxy. The scale is logarithmic, by the way. That's important. Type 2 isn't just a bit more powerful than Type 1, it's billions of times more powerful. And Type 3 is billions of times more powerful than Type 2. We're talking about differences so vast they almost break comprehension. But here's the uncomfortable part. The part Kardashev himself understood when he created this scale. Humanity doesn't fit neatly into any of his 3 categories. We're not Type 1 yet. We're not even close. We're something else, something earlier on the ladder, and understanding exactly where we stand, that's where things get humbling. So where does humanity stand on Kardashev's scale? We're Type 0.73, not Type 1, not even Type 1 in progress. We're Type 0, with a decimal. We're still in the tutorial level of cosmic civilization, and that number, 0.73, tells a very specific story about where we are right now. Let me put this in perspective. Humanity currently consumes about 18 terawatts of power globally. That's 18 trillion watts. Every power plant, every car engine, every device plugged into a wall socket, every fire burning, every solar panel, all of it combined equals about 18 terawatts. That sounds like a lot, and for us it is. It powers our cities, our industries, our entire modern civilization. But compared to what's available on Earth, compared to what a true Type 1 civilization would harness, we're barely scratching the surface. Earth receives about 174,000 terawatts of solar energy from the sun. every second. Most of it just bounces off into space or gets absorbed by oceans and atmosphere without us ever using it. We're capturing and using roughly 1/100th of 1% of what hits our planet. And that's just solar. That doesn't count the geothermal energy from Earth's core, the kinetic energy in our oceans and atmosphere, the tidal forces from the moon. All that energy is there, available, governed by physics we understand. We're just not using it yet. Here's what Type 0 really means. We're still dependent on dead plants, fossil fuels, coal, oil, natural gas. These are all ancient organic matter, compressed and transformed over millions of years. We're digging up the past and burning it. About 80% of our energy still comes from these sources. The other 20%? Nuclear fission, hydroelectric dams, wind turbines, solar panels, geothermal plants. We're diversifying, sure, but slowly. Very slowly. We're a planetary civilization in training wheels. Think about what that means. We can't control our climate. We can barely predict our weather more than a few days out. Earthquakes, hurricanes, volcanic eruptions. These are things that happen to us, not things we manage. We fight wars over resources, oil, water, rare earth minerals, because we haven't figured out how to access the abundant energy all around us efficiently enough to make scarcity obsolete. We're confined almost entirely to one planet. Sure, we've sent a dozen people to the moon. We've got some robots on Mars, but we couldn't survive anywhere else in our solar system without constant resupply from Earth. From a cosmic perspective, we're infants, learning to crawl, looking up at mountain climbers in the distance. But here's the thing, we're moving, we're climbing, just very, very slowly compared to the scale of the ladder above us. Let's get some historical perspective here. For most of human history, we were Type 0 point nothing, hunter-gatherers burning wood and animal fat. Our energy consumption was essentially biological. The food we ate, the fires we made. Then came agriculture, domesticated animals, water wheels, windmills. We started harnessing more than just our own muscles, but the energy scale was still tiny. The Industrial Revolution changed everything. Suddenly we were burning coal at massive scales, powering steam engines, factories, trains. Energy consumption started climbing exponentially. Then oil, electricity, internal combustion engines, nuclear power. Each breakthrough pushed us higher on the scale. We've gone from wood fires to nuclear reactors in about 100,000 years of human history, and most of that progress happened in just the last 300 years. That's incredibly fast on evolutionary timescales. But here's what's interesting. Our rate of energy growth is actually slowing down now. For most of the 20th century, global energy consumption doubled every few decades. Exponential growth. If that had continued, we'd reach Type 1 status in just a couple of centuries. Simple math. But it's not continuing. Not at the same rate, anyway. Why? A few reasons. We're getting more efficient. Modern LED bulbs use a fraction of the power that old incandescent bulbs did. Electric cars are more efficient than gas engines. Better insulation, smarter grids, optimized manufacturing. Efficiency means we can do more with less, which is good for sustainability, but it slows our climb up the Kardashev scale. Because the scale measures total energy use, not efficiency. There's also the question of whether we even want to keep increasing consumption indefinitely. Climate change is forcing us to reconsider the fossil fuel addiction. Moving to renewables is necessary, but it's not driving the same explosive growth we saw in the coal and oil eras. So right now we're in this weird transitional phase, Type 0.73. Powerful enough to reshape our planet's surface, alter its climate, even destroy ourselves with nuclear weapons, but not organized enough, not advanced enough, to truly control our planetary systems, not advanced enough to eliminate resource scarcity, not advanced enough to become a multi-planet species yet. The gap between us and Type 1 is bigger than most people realize. We're not halfway there, we're not even a quarter of the way there, we're about 7% of the way there, if you're tracking by energy consumption. And the challenges aren't just technical, They're social, political, economic. How do you coordinate global energy infrastructure? How do you distribute that power fairly? What happens to nations, borders, economies when energy becomes essentially unlimited? Who controls the planetary thermostat when we can actually control the weather? These aren't science fiction questions anymore. They're questions we'll have to answer if we want to reach Type 1. But here's the hopeful part. We are on the ladder. That matters. We understand physics well enough to know what's possible. We have the technology roadmap, even if we're still working out the details. Fusion power, space-based solar arrays, advanced geothermal. These aren't fantasies. They're engineering problems. Difficult engineering problems, but solvable ones. We're Type 0.73. Still dependent on our planet. Still vulnerable to our own technology. Still learning how to work together on a global scale. But we're climbing. Every solar panel installed, every fusion reactor experiment, every step towards sustainable energy, it's progress. Slow progress, maybe, but progress nonetheless. The question is, what does the next rung of the ladder actually look like? What happens when a civilization crosses that threshold? When they finally harness all the energy of their planet? What does a true Type 1 civilization look like? Imagine waking up one morning and checking the weather forecast, not to see what the weather will be, to decide what you want it to be. Need rain for the crops in California? Done. Want to prevent a hurricane from forming in the Atlantic? No problem. Feel like it should be 72 degrees and sunny across the entire northern hemisphere this weekend? Consider it handled. That's Type 1. That's what it means to truly master your planet's energy. We're not talking about better solar panels or more efficient batteries. We're talking about a civilization that has harnessed every available joule of energy on their world, every ray of sunlight that touches their planet, captured and used, every bit of geothermal heat rising from the core tapped into, every gust of wind, every ocean current, every tidal pulled from their moon, all of it controlled, all of it productive. Kardashev's original calculation put Type 1 at about 1016 watts of power. That's 10 followed by 16 zeros, 10 million, billion watts. Modern refinements suggest it's closer to 10 or 17 watts when you account for everything a planet receives and generates. But the exact number matters less than what it represents. Total planetary energy mastery. Let's break down what that actually means, because it's not just about having really good power plants. First, solar energy. A Type 1 civilization doesn't just have solar panels on rooftops, they have solar collection infrastructure across their entire planet. Deserts covered in photovoltaic arrays, orbital solar stations beaming power down to the surface. They're capturing not just some of the sunlight that hits their world, but essentially all of it that isn't needed for natural ecosystems. And they're doing it efficiently enough that energy storage and transmission are solved problems. No blackouts, no grid failures. Power flows to wherever it's needed, instantly, with minimal loss. But it goes beyond solar. Geothermal energy, Earth's core is hot, really hot, about 5200 degrees Celsius at the centre. That heat is constantly radiating outward, and most of it just dissipates into space or stays locked in the mantle. A Type 1 civilization taps into that. Deep drilling, advanced heat exchangers, maybe even direct access to magma chambers. They're not just using the shallow geothermal that we can access today, they're drinking from the planet's core. And here's where it gets really interesting. Weather control. Think about how much energy is in a hurricane. The heat energy released by a single large hurricane is equivalent to about 200 times the entire world's electrical generating capacity. Every second, for days. A Type 1 civilization doesn't run from hurricanes, they prevent them from forming in the first place. Or if they need to move heat around the planet, they create them deliberately and steer them exactly where they want. They can manage atmospheric circulation, control rainfall patterns, prevent droughts or floods, not by wishful thinking or cloud seeding, by having enough energy to actually move air masses to heat or cool regions of atmosphere to manage the thermal dynamics of their entire planet. Same with earthquakes. Now, you can't prevent all seismic activity. The planet's geology is what it is, but you can monitor stress in fault lines, and you can relieve that stress in controlled ways before it builds to catastrophic levels. Tiny, managed releases instead of devastating quakes. You can stabilize volcanic activity, again not by suppressing it entirely, but by understanding and managing the pressure in the mantle and crust. A Type 1 civilization doesn't just live on their planet, they actively manage it. The planet becomes less a home you're subject to and more a machine you operate, and that opens up possibilities we can barely imagine from our Type 0 perspective. Terraforming. Not of their home world, obviously, that's already habitable, but of other worlds in their star system. Mars? Give them a few centuries. They have the energy budget to thaw the ice caps, to generate a magnetic field, to create an atmosphere. It's not easy, but it's doable with enough power. Venus. Harder, but theoretically possible. They could build sunshades, cool the planet, process the atmosphere. Moons of Jupiter or Saturn. Underground oceans on Europa could be accessed. Titan's atmosphere could be modified. A Type 1 civilization isn't confined to one planet anymore. There are multi-world species, not just because they can travel between planets, but because they can make those planets livable. They can build massive space infrastructure, orbital habitats, space elevators, mining operations on asteroids, manufacturing in zero gravity. All of this requires enormous amounts of energy, and they have it. Resource scarcity becomes obsolete, at least for energy and materials, when you can mine asteroids, when you can synthesize whatever you need given enough. Power, when you can recycle at nearly perfect efficiency. You're not fighting over oil deposits anymore. Now, this doesn't mean Type 1 civilizations are utopias. The Kardashev Scale measures energy capability, not wisdom or social organization. You could theoretically have a Type 1 civilization that's deeply divided, or authoritarian, or dysfunctional in 1,000 other ways. But the energy abundance does change the equation. A lot of human conflict is about resources, energy, food, water, land. When those aren't scarce anymore, the reasons for conflict shift. So what's the timeline? How long would it take us to get from Type 0.73 to Type 1? Freeman Dyson, the physicist who came up with the Dyson sphere concept we'll talk about later, did some calculations. If we maintained exponential growth in energy consumption at the rate we had in the mid-20th century, we could hit Type 1 in about 200 years. But as we talked about earlier, that growth has slowed. We're getting more efficient, which is good for the planet but slows the climb. More realistic modern estimates put it at somewhere between 200 and 400 years. Maybe longer if we prioritize sustainability over growth. Maybe faster if we make major breakthroughs in fusion power or space-based solar. But there are challenges, big ones. The technical challenges are actually the easiest part. We know the physics. We understand how to build better solar panels, how to drill deeper for geothermal, how to capture wind and tidal energy more efficiently. Fusion power is hard, but it's not impossible. We're making progress. The harder challenges are organizational. How do you build a global energy grid? Right now we have national grids, regional grids. They barely talk to each other. A Type 1 civilization needs planetary coordination. How do you distribute that energy fairly? Who decides where the power goes? Who manages the weather control systems? These are questions of governance, not engineering. What happens to existing power structures? National governments, corporations, economic systems. They're all built around resource scarcity and energy limitations. What happens when those limitations disappear? And there's a darker question lurking underneath all of this. We're powerful enough right now to destroy ourselves. Nuclear weapons, climate change, biological weapons, potentially artificial intelligence gone wrong. We have the power to end human civilization, but we're not organized enough, not wise enough yet, to definitely prevent those outcomes. The transition from Type 0 to Type 1 is the danger zone. You're powerful enough to be dangerous, but not stable enough to be safe. If there's a great filter, a reason why we don't see advanced civilizations all over the galaxy. This might be it. This narrow window where civilizations either figure out how to work together on a planetary scale or they destroy themselves. We're in that window right now. But if we make it through, if we solve the coordination problems, avoid the catastrophes, and reach true Type 1 status, then we're ready for the next step, the step that sounds completely impossible from where we're standing right now. Because once you've mastered your planet, once you've harnessed every bit of energy your world can provide, there's only one place left to look for more power. Up, to the star that's been providing most of that energy all along. And that's where things get really interesting. The sun puts out 3.8 to 10 to the 26 watts of power. That's 380 septillion watts every second, in all directions. Most of it just radiating into empty space, never touching anything, never being used. Earth intercepts a tiny fraction of that. We're about 93 million miles away, and we're a small target. We catch maybe 1 part in 2 billion of the sun's total output. And even that tiny fraction is more than enough to power all life on our planet, drive our weather, warm our oceans, grow our crops. Now imagine capturing not just the fraction that hits Earth. Imagine capturing all of it, every photon, every direction, the entire output of the star. That's Type 2. And the difference between Type 1 and Type 2 isn't incremental. It's not like going from a small power plant to a big one. It's going from planetary energy to stellar energy. It's a jump of 10 billion times more power. With that much energy, you're not managing one planet anymore. You're managing a solar system. You can move worlds, create artificial planets, support not billions of people but quadrillions. You can build structures so massive they're visible from other star systems. You become, by any reasonable definition, a stellar civilization. But here's the question everyone asks. How? How do you actually capture a star's energy? The answer is one of the most famous concepts in all of science fiction and speculative science. And it comes from a physicist named Freeman Dyson, working in 1960. The Dyson sphere. Now, when most people hear Dyson sphere, they imagine a solid shell built around a star, a massive ball completely enclosing the sun, with people living on the inside surface. That's not what Dyson proposed, and it's not what would actually work. A solid shell around a star is physically impossible. The gravitational forces would rip it apart. There's no material strong enough. The engineering is a nightmare, and even if you could build it, it would be gravitationally unstable. Any small push, and it would drift into the star. What Dyson actually described was a swarm. Millions, maybe billions, of independent satellites orbiting the star at various distances, each one collecting solar energy, each one converting that energy into a form that can be transmitted elsewhere, covering the star from every angle but not as a single structure, a Dyson swarm. Think of it like a cloud of solar panels, each one the size of a small country, all orbiting the star in carefully calculated paths so they don't collide. Some close in, near the equivalent of Mercury's orbit, some farther out, near Earth's orbit or beyond. Different distances, different orbits, but all working together. From a distance, looking at this star, you wouldn't see a star anymore. You'd see something that glows, but mostly in infrared, because the swarm would absorb most of the visible light, heat up, and radiate in the infrared spectrum. That's actually how we might detect one. We're looking for stars that seem to glow too brightly in infrared and too dimly in visible light. Unnatural emission spectra. But let's back up. How do you actually build something like this? First, you need raw materials. A lot of raw materials. You need to disassemble something. Mercury is the usual answer. It's the closest planet to the sun, so it's easiest to reach. It's metal rich. And honestly, nobody's going to miss it. It's not habitable. It's not particularly useful for anything except mining. So you send self-replicating mining robots to Mercury. Von Neumann machines, we call them. Robots that can build more robots. They land on Mercury, start mining, start processing the metals and materials. They build solar collectors. They build more copies of themselves. The process accelerates exponentially. One machine becomes two, two become four, four become eight. Before long, you have millions of machines, all mining, all building, all launching new satellites into orbit around the Sun. The timeline? If you've got the technology, you could theoretically complete a Dyson swarm in somewhere between 50 and 100 years once you start. That's fast on cosmic scales. Of course, that assumes you've already reached Type 1. You need massive industrial capacity, space infrastructure, the ability to coordinate this project across your entire civilization. But if you've got all that, then yes, a century or so. And once it's complete, once you've wrapped your star in energy collectors, you can do things that sound like magic, move planets, literally. With enough energy, you can build massive engines or use directed energy to alter a planet's orbit. Rearrange your solar system however you want. Create artificial worlds, not terraformed planets, entirely artificial habitats, Stanford Tory, O'Neill cylinders, whatever design you prefer. You have the energy to build and maintain them, to spin them for gravity, to light them, to support ecosystems inside them. You could support quadrillions of individuals, not just humans or whatever species you are, but the energy budget allows for populations that would cover every surface of every planet in your original system and still have room to grow. Interstellar travel becomes feasible. Real interstellar travel, not the tiny probes we're planning now. With a Type 2 energy budget, you can accelerate massive ships to a significant fraction of light speed. You could send generation ships, hibernation ships, even entire mobile habitats to other stars, and you become visible, very visible. A completed Dyson swarm is not subtle. If there's a Type 2 civilization within a few thousand light years of us, we should be able to detect it. The infrared signature would be unmistakable. A star that's too dim in visible light and too bright in infrared, with a spectrum that doesn't match any natural phenomenon. We're actively looking for these signatures. The search for Dyson spheres is a real part of modern SETI work, and we've found candidates, strange signals that make us look twice. The most famous is Tabby's star, KIC 8462852, if you want the catalogue number. It's about 1,470 light-years away in the constellation Cygnus. In 2015, astronomers noticed something weird. The star was dimming, not in a regular pattern like an orbiting planet would cause, irregularly, sometimes by up to 22%, which is huge. No planet does that. Some scientists pointed out that the dimming pattern could be consistent with a partial Dyson swarm under construction. Something massive orbiting the star in irregular patterns. The internet went wild. Have we found an alien megastructure? Probably not. The most likely explanation now is dust clouds or a swarm of comets, possibly from a disrupted planet or a collision in the system, natural phenomena that just happen to create weird dimming patterns. But here's what Tabby's star taught us. It showed us what to look for. It showed us that we can detect anomalies, that we have the tools to spot something artificial if it's out there. And it reminded us that the universe is full of strange natural phenomena that can look artificial until you study them closer. We haven't found a confirmed Dyson sphere yet. We've looked at hundreds of thousands of stars. We've found weird signals, strange spectra, unexplained dimming, but nothing that definitively says, this is artificial. This is a Type 2 civilization. Which brings us back to that haunting question. Where are they? If Type 2 civilizations exist, if they're building Dyson swarms around their stars, we should see them. The galaxy is 13.6 billion years old. Stars like our Sun have been around for billions of years. If even a fraction of those stars hosted life, if even a small percentage of those civilizations survived to Type 2, the galaxy should be full of them. It's not, or at least we can't see them yet. Maybe we're looking in the wrong places. Maybe Dyson swarms aren't the optimal design, and they're doing something else we can't recognize. Maybe they're hiding deliberately, or maybe the jump from Type 1 to Type 2 is harder than it seems from our Type 0 perspective. Think about what it would take. You've unified your planet, solved your resource problems, achieved stable governance, avoided destroying yourselves. That's Type 1. Now you need to maintain that stability and coordination for thousands of years while you expand into your solar system, while you disassemble a planet, while you build a megastructure around your star. That's a lot of time for something to go wrong. A lot of time for civilizations to stagnate, or collapse, or simply lose interest. The timeline from Type 1 to Type 2 is anyone's guess. Maybe 1,000 years if they're ambitious and everything goes right. Maybe 10,000, maybe longer. Or maybe, and this is the dark possibility, maybe most civilizations never make it to Type 2. Maybe there's a filter, something that stops them. But if they do make it, if a civilization successfully becomes Type 2, then they're ready to think even bigger. Because wrapping one star in collectors is impressive, but there are billions of stars in a galaxy, and that's where Type 3 enters the picture. If you're a Type 2 civilization, you control the energy of your star. You've built a Dyson swarm. You've got quadrillions of individuals living across your solar system. You can move planets, build artificial worlds, send ships to other stars. You're powerful beyond anything we can currently achieve. But you're still limited. Limited to one star system. Limited to the energy of one sun. There are 200 to 400 billion stars in the Milky Way galaxy alone. Type 3 is when you harness them all. Now let me be clear about the scale we're talking about here, because the jump from Type 2 to Type 3 is even more staggering than the jump from Type 1 to Type 2. A Type 3 civilization controls somewhere between 1036 and 1037 watts of power. That's the combined output of hundreds of billions of stars, coordinated across a galaxy that's 100,000 light-years from edge to edge. This isn't just building more Dyson swarms. This is something fundamentally different. This is coordination across space and time that makes planetary governments look simple. Think about the communication problem alone. Light takes 100,000 years to cross the Milky Way. If you're a Type 3 civilization with outposts on opposite sides of the galaxy, any message between them takes 100,000 years. Each way, you send a message. 100,000 years later, they receive it. They send a reply. 100,000 years later, you get it. That's 200,000 years for a conversation. A conversation that starts before modern humans existed and ends in the present day. How do you coordinate anything across those distances? You can't have real-time control. You can't have centralized decision-making in any traditional sense. You'd need some form of distributed intelligence or autonomous systems that can operate independently for millennia while still working toward common goals. Or maybe quantum entanglement. If you could figure out faster-than-light communication, that would change everything. But as far as we know, that's not possible. Information can't travel faster than light. So a Type 3 civilization isn't really one unified entity. It's more like millions of interconnected civilizations, each one potentially Type 2 in its own star system, all working together across incomprehensible distances and timescales. They're not planning in years or decades or even centuries. They're planning in millions of years. And what can they do with that kind of power and reach? Stellar engineering. Not just moving planets within a system, but moving stars themselves. Stars orbit the galactic center. Those orbits are determined by gravity, by the distribution of mass in the galaxy. But with enough energy, you could alter a star's trajectory. Gradually, over thousands or millions of years, you could move it wherever you want. Why would you do that? Maybe to cluster stars for easier travel between them. Maybe to avoid future collisions or dangerous regions of the galaxy. Maybe to create stable zones for long-term habitation. A Type 3 civilization could practice stellar husbandry, managing their star population like a gardener manages trees. They could build structures on galactic scales. Not individual Dyson swarms around single stars, but networks connecting thousands or millions of stars. Relay stations for communication or energy transmission. Transit systems using wormholes or warp drives, if those are possible. They could manage black holes, the supermassive black hole at the center of the Milky Way, Sagittarius A, contains about 4 million solar masses. The energy from matter falling into that black hole, or from the rotation of the black hole itself, a Type 3 civilization could potentially tap into that. Black holes could be power sources, or they could be used for computation. Some theories suggest you could use the extreme physics near a black hole's event horizon for incredibly efficient information processing. A Type 3 civilization could potentially manipulate dark matter or dark energy. We barely understand what those are, but they make up 95% of the universe's mass energy. If you could interact with them, control them. The possibilities are beyond our current physics. They might be able to resist the heat death of their galaxy. The universe is expanding, cooling. Eventually all stars will burn out, all black holes will evaporate, and everything will reach maximum entropy. Heat death. But a Type 3 civilization, with energy control on galactic scales, might find ways to fight that, at least locally, at least for a lot longer than natural processes would allow. They could create safe zones, regions of the galaxy managed for long-term stability, protected from supernovae, gamma-ray bursts, stellar collisions, maintained across billions of years. And here's the key thing about Type 3. If they exist anywhere in our galaxy, we should see them. You can't hide a galactic civilization. The sheer scale of the infrastructure, the energy signatures, the engineering projects, it would be obvious. You'd see patterns in star movements. Stars don't naturally cluster in certain ways or move in coordinated patterns. If you saw that, you'd know something was causing it. You'd see massive infrared signatures, not just from one star, but from thousands or millions of stars, all showing that characteristic Dyson swarm spectrum. You'd see unexplained structures, vast objects that don't match any natural phenomenon, patterns in gamma-ray emissions maybe, or organised voids in space, and we see nothing. No coordinated star movements, no galaxy-spanning infrared signatures, no obvious megastructures at galactic scales. The Milky Way looks natural, random, chaotic in the way you'd expect from pure physics and gravity, with no intelligence shaping it. So either there are no Type 3 civilizations in our galaxy, or they're very good at being invisible, but why would they hide? At Type 3, what would you be afraid of? Maybe there's a predator, something that hunts advanced civilizations, the dark forest hypothesis, the idea that the universe is full of predators and anyone who reveals themselves gets destroyed, so everyone stays silent, stays hidden. That's a dark thought. But it's one explanation. Or maybe Type 3 civilizations transcend physical form. Maybe they upload themselves into virtual realities, into computronium, into forms we can't detect because they're not interacting with normal matter anymore. Maybe they've figured out how to leave this universe entirely, access other dimensions, other planes of existence. Or maybe the jump from Type 2 to Type 3 is just too hard. Maybe no civilization makes it that far. Think about the timeline. How long would it take to go from Type 2 to Type 3? You've got your home star system fully developed. Now you need to reach other stars, even at 10% of light. Speed, which is incredibly fast, it takes 40 years to reach the nearest star. Then you need to build infrastructure there. Another Dyson swarm, habitats, industrial capacity. That takes time, decades at least, maybe centuries. Then you move on to the next star, and the next, and the next. Even if each new star system only takes 100 years to develop fully, and even if you're expanding in all directions at once, colonizing 100 billion stars takes, well, it depends on your model. If you're expanding as a wave, with each new system sending out colony ships to multiple other stars, it's exponential growth. The classic calculation says you could colonize the entire galaxy in about 10 million years at sublight speeds. 10 million years sounds like forever to us, but it's nothing on cosmic timescales. The galaxy is 13.6 billion years old. Stars like the Sun have existed for 8 or 9 billion years. If intelligent life is even remotely common, if civilizations reach Type 2 even, occasionally, then there should have been plenty of time for at least one of them to expand across the galaxy. But we don't see evidence of that expansion. We don't see a colonization wave. We don't see Type 3. This is the Fermi paradox at its most acute. Where is everybody? Maybe we're the first. Maybe we're early in the universe's timeline for intelligence to emerge. Maybe all the previous generations of stars didn't have the right conditions, didn't have enough heavy elements, didn't produce stable enough systems for life to develop and persist. Maybe we're rare. Maybe the jump from single-celled life to intelligence is so improbable that we're one of only a handful of technological civilizations in the galaxy. Maybe there's a great filter ahead of us, something that stops civilizations before they reach Type 3, before they even reach Type 2. Maybe we're about to find out what it is, or maybe they're out there and we're just not recognizing the signs. Maybe Type 3 civilizations operate in ways so different from what we expect that we're looking right at them and not seeing them. But one thing is clear. If Type 3 civilizations exist in our galaxy, they're either hiding extremely well, or they've transcended in ways we don't understand, or they don't exist yet. And that has profound implications for where humanity might be headed. Because Type 3 was as far as Kardashev's original scale went. 3 types: Planetary, Stellar, Galactic. That seemed to cover the reasonable possibilities. But some scientists looked at Type 3 and asked, why stop there? What comes after you've mastered a galaxy? And that's where things get really speculative. Kardashev stopped at 3. Type 1, planetary energy. Type 2, stellar energy. Type 3, galactic energy. That was his scale, 3 types. And honestly, Type 3 seemed like a reasonable place to stop. If you can harness an entire galaxy, what else is there? Well, some scientists couldn't leave it alone, because there are more galaxies, billions of them, hundreds of billions in the observable universe alone. And the universe itself has energy, lots of it. So in the decades after Kardashev proposed his scale, others extended it, added new types, pushed the boundaries of what might be possible. These aren't part of Kardashev's original work, and they get increasingly speculative, increasingly philosophical, increasingly difficult to distinguish from fantasy. But they're worth talking about, because they help us think about ultimate limits, about what the laws of physics might allow at the most extreme scales. Type 4, Universal Civilization. This is a civilization that has expanded beyond a single galaxy to harness the energy of the entire observable universe. We're talking about 1049 watts of power or more, 2 trillion galaxies, each containing hundreds of billions of stars, all under the control of one vast civilization. The energy is almost beside the point at this scale. The real question is, how? The observable universe is 93 billion light-years across, and it's expanding. Faster than light, in fact, due to the expansion of space itself. Distant galaxies are receding from us at speeds greater than light, which means there are parts of the universe we can never reach. Ever. Even if we travelled at the speed of a light, we'd never catch up to them. The expansion is too fast, so a Type 4 civilization would need to circumvent that somehow. Faster than light travel, wormholes, warp drives, some way to cheat the cosmic speed limit, and that requires physics we don't have yet. Maybe physics that's impossible, we don't know. If you could do it though, if you could somehow coordinate across the entire universe, you'd be manipulating space-time itself, creating and stabilizing wormholes, bending space to make distant regions accessible. You wouldn't just be using the universe's energy, you'd be restructuring the universe to suit your needs. You might be able to prevent the heat death of the universe, or at least delay it significantly, manage entropy on cosmic scales, keep usable energy available long after natural processes would have ground everything to a halt. You could create universes, in theory. If you have enough energy and control over fundamental forces, you might be able to generate new universe bubbles, pocket universes with their own physical laws. At this point, we're crossing the line from physics into metaphysics. Type 4 isn't about practical engineering anymore, it's about theoretical limits, about what might be possible if there are no limits. And then there's Type 5, multiverse manipulation. If Type 4 controls one universe, Type 5 controls multiple universes, the entire multiverse if such a thing exists. This assumes the multiverse is real, which is debatable. Some interpretations of quantum mechanics suggest infinite parallel universes. Some cosmological models suggest bubble universes with different physical constants. Some theories of eternal inflation suggest an infinite fractal of universes spawning forever, but we have no evidence for any of this, no way to observe other universes, no way to test these theories. A Type 5 civilization, in theory, could move between universes, access parallel realities, manipulate the fundamental constants that govern physics in each universe. Want a universe where the speed of light is faster, where gravity is weaker, where time flows differently? A Type 5 civilization could supposedly create that, or find it and move there. They could harvest energy from the birth and death of universes, manipulate the quantum foam that might generate new realities, exist outside of any single timeline or physical framework. This is so far beyond anything we can meaningfully discuss that it barely qualifies as science. It's philosophy dressed in physics terminology. Some people have proposed even higher types, Type 6, 7, Omega, civilizations that transcend physical reality entirely, that manipulate mathematical laws, logical structures, the very fabric of existence itself. At that point, you're just describing gods, omnipotent beings that exist beyond comprehension. There's no meaningful difference between a Type Omega civilization and divinity. So why talk about these at all? Because they push our thinking. They force us to consider what limits actually exist, where the boundaries of physics really are, what's genuinely impossible versus just really, really hard. They also reveal something important. Energy becomes less useful as a metric at extreme scales. Kardashev's insight was brilliant for Types 1, 2, and 3. Energy consumption is measurable, observable, directly correlated with capability. But at Type 4 and beyond, energy isn't the constraint anymore. The constraints are physics itself, information processing, entropy, the structure of space-time. So some scientists have proposed alternative scales. The Barrow scale, for example, measures how finely a civilization can manipulate matter. Can you control bulk matter, molecular structures, atoms, subatomic particles, the quantum foam of space-time itself? Information-based scales measure computational capacity. How much information can you process? How efficiently? Can you simulate entire universes? Run consciousness on quantum computers? Complexity scales measure how much organization you can maintain against entropy. How complex are your structures? How long can you keep them running? These might be more useful for understanding truly advanced civilizations, because at some point, it's not about how much energy you have, it's about what you can do with it, how you process information, how you manipulate reality at its most fundamental levels. But here's the thing, all of these extensions beyond Type 3, they're speculation, fun speculation, useful for thought experiments, good for exploring theoretical limits. But we have no evidence that any of it is possible, no observation of Type 4 civilizations, no mathematical proof that the multiverse exists, no physics that allows faster-than-light travel. Kardashev's original 3 types are grounded in known physics. Difficult, yes. Requiring technology we don't have yet, yes, but not impossible. Not violating any laws of nature we understand. Type 4 and beyond. They require physics we don't have. Maybe physics that doesn't exist. So when we talk about the Kardashev scale in practical terms, when we think about what we might actually detect when we consider humanity's future, we focus on Types 1, 2, and 3. Those are the meaningful categories, the ones that matter for understanding where we are and where we might go. But the higher types serve a purpose. They remind us how much we don't know, how small our understanding is, how vast the possibilities might be. And they lead us to one of the darkest questions in all of science. If these advanced civilizations are possible, if even just Type 2 and Type 3 are achievable with physics we already understand, then why don't we see them? Where is everybody? And whatever's stopping them from filling the galaxy, are we about to encounter it ourselves? There's a concept in the search for extraterrestrial intelligence that keeps scientists awake at night. It's called the Great Filter, and understanding it changes how you think about the Kardashev Scale. Because the scale isn't just a measurement system, it's a ladder, and something might be preventing civilizations from climbing it. The Great Filter was proposed by economist Robin Hanson in 1996. The logic is straightforward and deeply unsettling. The universe is old. 13.8 billion years. The Milky Way has been forming stars for most of that time. There are hundreds of billions of stars in our galaxy, many with planets, many of those planets in habitable zones. If life and intelligence are even moderately common, the galaxy should be full of advanced civilizations by now. We should see Type 2 and Type 3 civilizations everywhere. Dyson swarms, stellar engineering, galaxy-spanning infrastructure. We see nothing. So something is filtering out civilizations, preventing them from becoming visible, spacefaring, galaxy-spanning. There's a bottleneck somewhere between simple matter and advanced civilization. A filter so effective that almost nothing gets through. The question is, where is that filter? Is it behind us? Something incredibly rare that we've already passed? That would be good news. It would mean we're special, lucky, perhaps alone in our galaxy. It would mean the hard part is over. Or is it ahead of us? Something that destroys almost all civilizations before they become Type 2 or 3? That would be very bad news. It would mean we're probably doomed, that we're about to hit the same wall that killed everyone else. Let's look at possible filters behind us first. The hopeful possibilities. Maybe abiogenesis is incredibly rare, the jump from non-living chemistry to living cells. We don't know how that happened on Earth. We know it happened at least once, about 3.8 billion years ago. But maybe it's so improbable that it almost never happens. Maybe Earth is one of the only places in the galaxy where life began at all. Or maybe simple life is common, but complex life isn't. Earth had single-celled organisms for 3 billion years before anything more complicated showed up. 3 billion years of just bacteria and archaea. That's a long wait. Maybe most planets never make that jump. Maybe complex multicellular life is the rare thing, and we're one of the few exceptions. Maybe intelligence is rare. Evolution doesn't automatically trend toward intelligence. It trends toward whatever survives and reproduces. Intelligence is expensive. Big brains need lots of energy. They're only worth it in specific circumstances. Maybe most planets with life never evolve anything smarter than, say, dolphins. Smart enough to survive, not smart enough to build technology. Or maybe technological civilization is the filter. Tool use, fire, agriculture, writing, science. Maybe the specific sequence of developments that leads to technology is so improbable that it almost never happens. If the filter is behind us, if any of these early steps are incredibly rare, then we're extraordinary. We're the lottery winners, and we have a clear path ahead to becoming a Type 2 or 3 civilization, because nobody else has gotten this far. But there's another possibility, one that's harder to ignore when you look at where we are right now. Maybe the filter is the transition from Type 0 to Type 1. Maybe this is where civilizations die. Think about our current situation. We're Type 0.73. We have enough technology to destroy ourselves several times over. Nuclear weapons that could end civilization in an afternoon. Climate change that could make Earth barely habitable. Biological weapons that could engineer pandemics far worse than anything natural. Artificial intelligence that might, if we're not careful, decide it doesn't need us. We're powerful enough to be dangerous, but we're not organized enough to be safe. We have global scale problems, but we don't have global scale coordination. We're divided into nations, corporations, ideologies. We compete for resources. We struggle to cooperate even when extinction is on the line. And this might be universal. This might be what happens to every civilization around Type 07. You develop world-destroying capabilities before you develop world-uniting wisdom. And most civilizations don't make it through. They destroy themselves. Nuclear war, environmental collapse, engineered plague, AI alignment failure, something. There are so many ways to die at this stage, and the window is narrow. We're in it right now. The next 100 to 200 years. This is when we either figure out how to work together as a planetary civilization, or we don't. If we don't, we join all the other dead civilizations, silent, invisible, just another filter statistic. If the Great Filter is here, at the Type 0 to Type 1 transition, it explains everything. It explains why we don't see Type 2 civilizations. Because almost nobody gets past Type 0. They all die in this narrow window of vulnerability. It explains the Fermi paradox, the silence of the cosmos, not because intelligence is rare, but because survival is rare. And it means we're in the most dangerous period in human history. Right now. Not because we're at war, not because of any specific immediate threat, but because we're at the stage where civilizations either make it or they don't. But let's say we make it through. Let's say we reach Type 1. We've unified, we've survived our own technology, we're stable and sustainable. Does the danger end there? Maybe not. Maybe there are filters ahead we can't even see yet. Maybe the transition to Type 2 is where civilizations fail. Some technical problem, some physical limit, some challenge we can't anticipate from our current perspective. Maybe advanced artificial intelligence kills its creators, not maliciously, just indifferently. Maybe every civilization creates AI, and every AI decides biological life is inefficient. Maybe there's something about stellar engineering that's fundamentally dangerous. Maybe building Dyson swarms attracts attention from something that hunts advanced civilizations, the dark forest hypothesis, the idea that the universe is full of predators and anyone who makes noise gets eliminated. Stay quiet, stay hidden, or die. That's a terrifying thought, but it would explain the silence. If there's something out there that destroys any civilization that builds megastructures that would filter out Type 2 and 3, or maybe time itself is the filter. Maybe civilizations that reach Type 2 simply lose interest in expansion. They build virtual realities and live in them. They upload their consciousness and stop caring about physical space. They don't colonize the galaxy because they don't want to. They're out there, they're advanced, but they're invisible because they've turned inward. Now, there are hopeful interpretations too. Maybe we really are early. The universe is 13.8 billion years old, but most of that time conditions weren't right for life like us. Not enough heavy elements, too much radiation, too unstable. Maybe the era of habitable planets only started a few billion years ago. Maybe we're among the first wave of technological civilizations. Maybe we're not seeing anyone because there's nobody to see yet. Maybe intelligence is so rare that we're alone in the Milky Way. Not alone in the universe, but alone in our region. The nearest other civilization could be in another galaxy, millions of light years away. Too far to see, too far to contact. Those are the hopeful thoughts. We're special, we're early, we're alone, but we'll make it. But the math is uncomfortable. If even 1 in a million stars produces a civilization that reaches Type 2, we should see them. The galaxy should have thousands of visible megastructures. If the filter is ahead of us, if something kills nearly all civilizations before they expand beyond their home system, that matches what we observe. Perfect silence, nothing visible. And we're about to find out which one is true, because we're climbing. Right now, we're at the point where the filter either is or isn't. The next few centuries will tell us. Either we make it to Type 1 and beyond, proving the filter is behind us, or we don't, becoming another invisible statistic in the silent galaxy. No pressure, but understanding this, understanding that we're potentially at the most critical juncture in human history, that what we do now might determine whether our species has a future at all. That changes things. That makes the stakes clear. The Kardashev Scale isn't just about energy, it's about survival. It's about whether we can grow up as a species fast enough to handle the power we've developed. And that brings us back to the question we started with. If advanced civilizations are out there, where are they? Why is the cosmos so silent? Let's look at the specific answers, the concrete possibilities, because the Great Filter is one explanation, but it's not the only one. So let's be specific about the silence. If Type 2 civilizations exist, we should see them. Dyson swarms create unmistakable infrared signatures, stars that look wrong, too dim in visible light, too bright in infrared, with emission spectra that don't match any natural process. We've surveyed hundreds of thousands of stars, we've looked at distant galaxies, we've analysed the light from millions of stellar objects, and we've found nothing. No confirmed megastructures, no obvious signs of stellar engineering, no Type 2 civilizations anywhere in our observable region. Type 3 should be even more obvious. Galaxy-spanning infrastructure, coordinated patterns in star movements, vast regions of space showing artificial organization. The Milky Way shows none of that. It looks exactly like you'd expect from pure physics. Stars orbiting the galactic center according to gravity. Random distributions. Natural chaos. So where is everybody? Let's walk through the possibilities, the explanations that might account for the silence. First possibility, they don't exist yet. Maybe we're early. The universe is 13.8 billion years old, but perhaps conditions for complex life only became favourable relatively recently. The earliest stars had almost no heavy elements, no carbon, no oxygen, no metals. You need those to build planets, to build chemistry, to build life as we know it. It took generations of stars living and dying, fusing heavier elements, scattering them through space before planets like Earth could form. That's billions of years right there. Maybe the window for habitable planets only opened a few billion years ago. Maybe Earth formed relatively early in that window. Maybe we're among the first civilizations to reach our level. If that's true, then we're not looking at a galaxy full of Type 3 civilizations. We're looking at a galaxy where most potential civilizations are still in early stages, or haven't emerged yet. We're the early arrivals. That's the hopeful interpretation. We're first. The cosmos is waiting for us to fill it. Second possibility. They exist, but they're hidden. The zoo hypothesis. Maybe advanced civilizations have found us. Maybe they're watching, but they've deliberately chosen not to interfere, not to reveal themselves. They're observing us the way scientists observe animals in nature reserves. No contact, no interference, just watching to see what we do. Why would they do that? Maybe there's a galactic code of ethics. Don't interfere with developing civilizations. Let them evolve naturally. Contact them when they're ready, when they've reached a certain threshold. Or maybe the dark forest theory is right. This one's darker. The idea is that the universe is full of civilizations, but everyone stays silent because speaking up is fatal. There are predators out there, advanced civilizations that destroy any competitors they detect. So everyone hides, everyone stays quiet. Any civilization that builds visible megastructures that broadcast its presence gets eliminated. In that scenario, we're walking through a dark forest, and any noise we make might attract something we don't want to meet. That would explain the silence perfectly. They're all there. They're just hiding. And maybe we should be too. Or maybe they've transcended physical form entirely, uploaded their consciousness into computers, created virtual realities far more interesting than physical space. They're not expanding across the galaxy because they don't need to. They're living in simulated worlds, experiencing whatever they want, and physical space is irrelevant to them. From our perspective, they'd be invisible. A few computers somewhere, running countless simulated realities. No Dyson swarms, no stellar engineering, no visible expansion. Third possibility, they existed and died. Maybe advanced civilizations are common, but they're unstable. They reach Type 1 or 2, thrive for a while, and then collapse. War, environmental disaster, AI catastrophe, resource depletion. Something kills them. On cosmic timescales, Civilizations might be brief, a few thousand years, maybe a few million years, and then they're gone, leaving no trace we can detect from light years away. If civilizations have short lifespans, then the galaxy could have hosted thousands or millions of advanced species over its history. But at any given moment, only a few exist. And the distances are so vast that we've never overlapped with them in time and space to see them. Fourth possibility, we're not looking correctly. This one keeps me humble. Maybe we're like ants trying to understand Wi-Fi. We're looking for radio signals, infrared anomalies, visible megastructures. But maybe Type 2 and 3 civilizations use technology so advanced we can't recognize it. Maybe they've figured out ways to manipulate space-time that don't create the signatures we expect. Maybe they've mastered physics we don't understand, yet. Maybe they're using communication methods we can't detect. We're searching with the tools we have. But those tools are primitive. We've only had radio telescopes for 60 years. We've only been seriously looking for exoplanets for 30 years. We've barely started searching. Maybe the evidence is there and we're just not seeing it. Not yet. Fifth possibility, distance and time. Space is really, really big. Even within our galaxy, stars are separated by light years. The average distance between stars is about 5 light years. That doesn't sound like much until you realize nothing can travel faster than light, and we can't even reach 1% of light speed with current technology. Even if there's a Type 2 civilization 1,000 light years away, we're seeing them as they were 1,000 years ago. If they just built their Dyson swarm 500 years ago, we won't see it for another 500 years. And we've only been looking seriously for about 60 years. That's nothing. That's less than a human lifetime. That's a blink on cosmic timescales. Maybe they're out there. Maybe we just haven't looked long enough, carefully enough in the right places. Sixth possibility, they're already here. This is where things get contentious. UAPs, unidentified aerial phenomena. There have been reports, some from credible sources, of objects doing things that don't match known technology, moving in ways that seem to violate physics as we understand it. Are those alien spacecraft? Are advanced civilizations already visiting Earth? The scientific consensus is probably not. Most UAP reports have mundane explanations: optical illusions, atmospheric phenomena, experimental aircraft, sensor glitches, the ones that remain unexplained. Well, unexplained doesn't mean aliens. It just means we don't know yet. Extraordinary claims require extraordinary evidence, and we don't have that evidence yet. No verified alien artifacts, no confirmed contact, just ambiguous reports and blurry footage. Could some of them be real? Could there be visitors we haven't confirmed yet? Maybe. But until we have solid evidence, we have to remain skeptical. The truth is, we don't know. We don't know why the cosmos is silent. We don't know where the civilizations are if they exist at all. The Drake equation tried to calculate how many civilizations exist in the galaxy, but the equation has so many unknowns, so many guesses, that you can plug in different values and get answers ranging from millions of civilizations to we're alone. We've learned a lot since Drake first wrote his equation in 1961. We know exoplanets are common now, billions of them in the Milky Way. We know the building blocks of life, organic molecules, are everywhere in space. But we still don't know how often life emerges, how often it becomes complex, how often it becomes intelligent, how often it survives long enough to become visible. Recent discoveries make the universe seem more hospitable for life than we thought, but that just makes the silence more puzzling. If conditions for life are common, where is everybody? We're still waiting for an answer, and while we wait, while we search, while we wonder, we're also making choices about our own future, about whether humanity will climb the ladder, about what kind of civilization we want to become. Because the Kardashev Scale isn't just about aliens, it's about us, our potential, our future. So what does this scale mean for humanity? What's our path forward? So where does all of this leave us? We're Type 0.73, still burning fossil fuels, still divided into competing nations, still figuring out how to survive our own technology, but we're climbing and understanding the scale, understanding where we are and where we could go. That matters, because the next few centuries will determine everything. Let's be specific about what reaching Type 1 would mean for humanity. Not in abstract terms, but in practical ones. It means the end of energy scarcity. Solar, wind, geothermal, fusion, all of it fully developed and integrated. Power flowing to wherever it's needed, whenever it's needed. No more energy poverty. No more resource wars over oil or coal. It means climate control. Not just mitigating climate change, but actually managing Earth's climate systems, preventing hurricanes, directing rainfall, maintaining stable temperatures. The planet becomes something we actively manage, not something that happens to us. It means space, colonization, permanent bases on the Moon and Mars, asteroid mining operations, orbital habitats. We become a multi-world species, no longer vulnerable to any single planetary catastrophe. It means post-scarcity for basic needs, energy, materials, food, water, abundant enough that no one goes without. That doesn't solve every human problem, but it removes a lot of the competition that drives conflict. The timeline? If we're optimistic, if we make the right choices, if we avoid destroying ourselves, 200 to 400 years to Type 1. That's 10 generations. Your great-great-great-great-great-great-great-grandchildren might live in a Type 1 civilization, but only if we survive the transition. The challenge isn't technical. We know how to build better solar panels, how to develop fusion power, how to capture geothermal energy. The physics is understood. The engineering is difficult but solvable. The challenge is coordination. How do we work together globally when we're used to thinking in terms of nations? How do we distribute resources fairly? How do we make decisions that affect the entire planet? And how do we survive the next 100 years without destroying ourselves? Because right now, we have the power to end civilization. Nuclear weapons, climate change, engineered pandemics, misaligned artificial intelligence. The tools of our own destruction are sitting right here, available, dangerous. We're in the filter zone, the danger window. And what we do now, the choices we make in the next few decades, they matter more than anything humanity has ever done. If we make it to Type 1, if we figure out how to coordinate globally and sustainably, then the path to Type 2 opens up. That's thousands of years away minimum. We'd need to fully colonize our solar system, establish industrial capacity on multiple worlds, develop the technology to build Dyson swarms, send the first self-replicating probes to Mercury or another metal-rich body. By the time we're ready for that, humanity might mean something very different. Genetic engineering, cybernetic enhancement, uploaded consciousness, AI-human hybrids. We might not recognize our descendants, but the journey starts now. Every solar panel we install, every fusion reactor experiment, every step toward international cooperation, every choice to build instead of destroy. Type 3, galactic civilization, that's millions of years away if it's possible at all. We can barely imagine what consciousness will look like by then, what form intelligence might take, whether physical bodies even matter anymore. But here's what's beautiful about the Kardashev Scale. It's not just a measurement system. It's not just a way to find aliens. It's a mirror. It shows us what we could become. It gives us a framework for thinking about humanity's potential. It helps us see past the immediate crises and conflicts to something larger. We're at the very beginning of the ladder, Type 0.73, barely climbing. Looking up at heights we can barely comprehend. But we're on the ladder. That's what matters. And whether we're alone in the galaxy or not, whether we ever meet another civilization or not, the scale gives us direction. It shows us what's possible if we can just survive long enough, grow wise enough, work together well enough. The cosmos is silent. We don't know why. Maybe we're the first. Maybe we're the only ones who made it this far. Maybe everyone else hit the great filter and died. Or maybe they're out there, hiding, waiting, watching to see if we make it too. Either answer is profound. If we're alone, then we're the universe's way of understanding itself. We're consciousness emerging from matter, capable of contemplating the cosmos that created us. That's extraordinary. That means everything we do, everything we become, matters in a way nothing else does. If we're not alone, if there are others out there, then first contact will be the most important moment in human history. Meeting another civilization, learning how they survived their filter, seeing what's possible at higher types, it would change everything we think we know. But until we find them, until we get an answer, we keep climbing, we solve our energy problems, we unify as a species, we expand into space, we survive our technology, we grow up, we become Type 1, then maybe, centuries or millennia later, Type 2, and maybe, just maybe, we become the civilization that someone else detects. We build our Dyson swarm, and some alien astronomer 1,000 light years away sees the infrared signature and wonders, are we alone? The Kardashev Scale isn't just about measuring civilizations, it's about potential, about what's possible when you think in cosmic terms, when you see yourself not as an individual or a nation, but as a species with a future stretching millions of years ahead. We're Type 0.73, still learning, still growing, still vulnerable, but we're climbing, and that's everything. Somewhere out there, maybe there's a Type 3 civilization watching our sun. Maybe they remember when they were where we are now. Maybe they're hoping we make it. Or maybe we're the first. Maybe the cosmos is waiting for us to fill it. Maybe we're the ones who'll build the first Dyson sphere, colonize the first galaxy, show the universe what intelligence can become. Either way, the ladder is there, the physics allows it, the potential exists. What happens next is up to us. If this changed how you think about humanity's place in the cosmos, subscribe to Night Space for more mysteries of the universe, and let me know in the comments, do you think we'll make it to Type 1? What's the biggest challenge we need to overcome? Where do you see humanity in 500 years? The climb continues, the future is unwritten, and the cosmos is waiting to see what we become.